We know that Coulomb's law tells us how we can calculate the electric force between any 2 point charges. But what happens when we have multiple charges? Well, what we're going to see is that what we need to do is simply do the vector addition problem that says add up all the individual force vectors acting on whichever charge you want to know the net electric force on. So let's look at a problem like this one. So we've got 3 charged particles that are fixed in the xy plane. Particle 1 carries a charge of -2 nanocoulombs and lies at the origin. Particle 2 carries a charge of +5 nanocoulombs and lies along the positive x-axis 4 meters away from the origin. Particle 3 carries a charge of -8 nanocoulombs and lies 3 meters directly below particle 2. What is the magnitude and direction of the net electric force exerted on particle 1 by the other 2 particles? So, for starters, there are now 3 particles, and I need to make sure it's absolutely clear which one I'm interested in calculating the net force on. So I'm going to be interested in the net electric force exerted on particle 1, which means I need to think about the forces that particle 1 feels. There's going to be a force acting on particle 1 caused by its interaction with particle 2. There's going to be a second force acting on particle 1 caused by its interaction with particle 3. So for starters, let me basically label, and again at the moment all I really care about is signs. And so I know I'm told in the problem that particle 1 is negatively charged, particle 2 is positively charged, particle 3 is also negatively charged. I also know that I'm going to need some distances. So if I'm interested in the interaction between particle 1 and particle 2, I'm going to need to know what's the distance that separates those 2 particles, and here I'm told that that distance is 4 meters. Again, when I think about the electric force between particle 1 and particle 3, I'm going to need their distance, the distance of separation between those 2 particles. And what I notice is I've got a right triangle, 4 meters along this side, 3 meters along this one, so I can Pythagorize square root of 3 squared plus 4 squared says that the distance separating particle 1 and particle 3 is 5 meters. Thinking ahead, I can probably recognize that while I'm also going to need to think about an angle here, that this line between particle 1 and 3, how far does that lie below the x-axis? And again, because I've got an adjacent side that's 4 meters, opposite side 3 meters, I can use the inverse tangent. An inverse tangent of opposite 3 meters over adjacent 4 meters tells me that this angle theta, as I've defined it here, is a 36.9 degree angle. So this line lies 36.9 degrees below the x-axis. Well, where do I start any force problem? I'm going to start with the free body diagram. Again, I need the free body diagram for particle 1. Particle 1 is negatively charged. The force particle 1 feels caused by particle 2, since particle 2 is positively charged, particle 2 is going to attract particle 1. So there will be a force exerted on particle 1 by particle 2. So here, notice again, we're using our subscripts to help us sort of label things out. So the electric force exerted on particle 1 by particle 2 is going to pull particle 1, or it's going to try to pull particle 1 to the right. Particle 1 is negatively charged, so is particle 3. So of course these two will repel. So when I think about the force particle 1 feels that's caused by particle 3, particle 3 is going to push particle 1 up and away from it. So I've got an electric force on particle 1 from particle 3 that points up in this direction. Well, now that I know what my 2 vectors are, I can pick a coordinate system and then go ahead and break them up into components so I can add them together. Again, because the electric force between particles has to lie along the line that connects them, right? I know that the electric force between particles 1 and 2 has to lie along the x-axis, and the electric force between particles 1 and 3 again has to make this angle theta with the x-axis. And so I know that this here is the angle theta. So the electric force exerted on particle 1 by particle 3 as it tries to repel it away from itself, is going to point at an angle theta above the negative x-axis. So let's break those force vectors up into components so we can add them together. Again, the net electric force I don't know, so I'm going to do the easiest thing and simply leave them in terms of x and y components. I've got my table set up the way we normally would, so I've got the net electric force equals what I'm going to choose to label force 2. So just sort of shorten this subscript, just keep the last term here. So force 2 plus force 3. Again, this is the force that I'm labeling force 3 in my equation. So we're setting up our table to break up our forces into components so that we can set up our equation. And our equation just says add together these two force vectors to get the net electric force acting on particle 1. Force 2 lies along the positive x-axis, so it's x components F2, all of it, y component 0. Force 3 has a negative x component, positive y component because it points up and to the left. Magnitude of force 3 is something that I'll calculate out in a minute, and again, the angle theta is the angle that that force vector makes with the x-axis, which means cosine theta goes with the x component, sine theta goes with the y. So if I've broken my vectors up into their components correctly, then it's easy enough to go ahead and set up my equation. So again, I'm saying the net force equals F2 plus F3, and so I have an x component equation and a y component equation. For my x component equation, I've got the x component of the net electric force acting on particle 1 equals all of F2 plus, and again here, this is sort of overkill, but I'm just emphasizing that I'm adding them together, and the x component for force 3 is negative. My y component equation says the y component of the net electric force acting on particle 1 is equal to 0 plus F3 sine theta. So there are my two equations. At this point, I know I want to solve for the x and y components of the net electric force. So now what I need to do is come back and calculate out the magnitudes of F2 and F3, and I can do that using Coulomb's law. So of course I know that the electric force between any two charges can be calculated K times the product of the absolute value of the charges divided by the distance between them squared. So if I want what I've labeled force 2, that's the interaction between particle 1 and particle 2. K again is my 8.99 times 10 to the 9th. I want the absolute value, so notice this is positive 2 times 10 to the minus 9. 5 times 10 to the minus 9, so I'm multiplying all that together on top, dividing by the distance between them squared. That was 4 meters, so this is 4 meters squared. And what that leaves me with, when I calculate it out, is 5.62 times 10 to the minus 9 newtons. So that's the magnitude of the force between particles 1 and 2. I can do the same thing for the magnitude of the force between particles 1 and 3. So now this is going to be K times the absolute value of Q1 times the absolute value of Q3 over the distance between particles 1 and 3 squared. K stays the same. Q1 stays the same. There's Q3, again, 8 times 10 to the minus 9, and again, because I want the absolute value, that's positively valued. The distance between particles 1 and 3, we calculated out right at the beginning. That was 5 meters, and so this is 5 meters squared. Plug all that into my calculator, I get 5.75 times 10 to the minus 9 newtons. So now I know what the magnitudes are for F2 and F3. I can come back to my equations and plug them in. So for my x component equation, plug in the magnitude of F2, plug in the magnitude of F3, plug in my angle theta, and my calculator tells me that the x component of the net electric force acting on particle 1 is 1.02 times 10 to the minus 9 newtons. Do the same thing for my y component equation. Here I only have F3 and theta to plug in, and my calculator says that this is 3.45 times 10 to the minus 9 newtons. A couple things you'll notice. One, again, they're forces, so they've got units of newtons. Two, both of these values are 10 to the minus 9, so these are really small, right? These are effectively nanonewton values. And then you'll notice that 1.02, 3.45, my y component is a little bit more than 3 times larger than my x component. So both of them are positive. Positive x component tells me to the right, positive y component tells me up, and it's got a y component that's a little bit more than 3 times larger than the x. If I want to know the magnitude of that, well, again, I can Pythagorize. So now that I know the x and y components of my vector, I can Pythagorize to get its magnitude. In this case, that happens to be 3.6 times 10 to the minus 9 newtons. Again, I can figure out which direction it points by defining some angle. So I'll pick phi to be the angle that my net electric force vector makes with the x-axis. That means I want the y component on top in my ratio inside the inverse tangent. I can plug in my component values, and I end up getting that angle phi is 73.6 degrees above the positive x-axis. So this is the game that we're going to play, sort of change the picture, change the values of the charges, change where they're located, but in terms of calculating the net electric force acting on one charge in a presence of other charges, it's just a vector addition problem. This is the process we're going to use over and over and over again in terms of solving for that.